Hey everybody, welcome back to Young Engineers of Today, the amazing Mechatronics edition. We're going to be continuing with Arduinos to no one's surprise. In this particular set of lessons, we're going to be going over inputs. Remember last Thursday that we did LEDs, and also last Tuesday, and then the Thursday before that, we spent a lot of time on LEDs, which was purely the output side of things. We set it up so that the LEDs blinked. We utilized for loops and arrays to make multiple LEDs blink in, a very simple pattern and things like that. I didn't really spend much time going over how you could modify for loops to do, special patterns and things, but that kind of stuff, you can do with some experimentation and things like that. I wanted to get over to the input side of things because obviously that's the other half of the equation when we're working with microcontrollers. There are plenty of circuits out there that exist that are solely output. That is to say that they affect LEDs or motors or speakers or whatever on a specific cycle that is unaffected by the environment around them, and that's perfectly legitimate. However, by introducing inputs, you increase the interactivity of your Arduino. You now have an Arduino that will be able to respond to outside stimuli. That is to say, you pressing a button, or somebody walking into your room, or the temperature changing, or whatever. So by doing that, you can actually increase the complexity of your circuits, you can increase the number of projects that you can use an Arduino for, and generally things just become a little bit more interesting. So I spent some time introducing inputs a little bit on Thursday, but it was more in the sense that I talked about digital versus analog. So I just wanted to check, you guys remember what those two are, what those two mean, what the difference between those two is, be, do? All right, no worries. Yeah, if you forgot, that's totally fine too. Yeah, that's no problem at all. So basically, if you remember, digital inputs have two values, or excuse me, digital in general has two values, either off or on, 0 or 1, hence why computers are referred to as digital, because they work in binary, zeros and ones, a sequence of on and off, or off and on, because a 0 represents off and a 1 represents on. So to expand upon that, and I'll just continue with this just in case anybody else has forgotten, to expand upon that, if you're sending power digitally, you're either sending all of the power you can possibly send or none of the power you can send, either full on or full off. And the reason why you might look at a graph of power sent over time and have these vertical lines is because the change is assumed to be instantaneous, like flipping the light switch in your bedroom. It's either on or it's off. There's no in between. On the other hand, analog can send either full on or full off, or it can send any range of values in between. So much like one of those dimmer switches on a light in like the dining room or something like that, or the living room, where you can turn the lights on full blast if you were so inclined. You can turn them down to like halfway. You can turn them back up to 75%. You can turn them down to nothing. You can turn them up to 30%. And all of that is a perfectly valid value in analog. So it's said that analog has an infinite number of values in its range because you can send 0.1 volts or 0.11 volts or 0.111 volts or 0.11111 volts and so on and so forth. So the difference between the two is digital has two possible values, whereas analog has an infinite possible number of values. And that's essentially the difference between the two. Analog is, I guess you could kind of say it's older than digital. That's not exactly correct to say, but a lot of electrical work and stuff like that, it's worked on some essentially sort of like analog. Digital's been around for a long time too. It's not like digital is some sort of new means of sending power or anything like that. If you've ever messed with let's see here. Well, a light switch, you've messed with digital. If you've ever used a gas pedal on a car, you've used analog. So again, that's just another analogy between the two. Anyway, we're going to spend the first circuit exploring analog inputs and seeing how the Arduino can handle that. In addition, we're also going to introduce ourselves to the serial monitor, which is going to be a very, 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 very important thing for Arduinos in the future. You may or may not get questions on the serial monitor in the Amazing Mechatronics competition. Unfortunately, I don't know enough about because there's always a semblance of secrecy kept to the questions that are going to be asked and stuff like that. So it may be that you'll never get anything for serial monitor. However, serial monitor is a very useful way of debugging an Arduino if you're ever working with it in person. So if you're building something that's more complex and you've deduced that maybe, I don't know, the problem with the Arduino is like in your circuit or whatever is on the software side, you can always set up some outputs for the serial monitor in order to keep track of what your program is doing and be able to debug it that way. Heck, if it's on the circuit side, if you know it's a hardware side, you can put in some different tracking mechanisms on the serial monitor, have them print out to the screen, and you can get a real-time update of what your Arduino is essentially thinking, what's going through its memory banks, and the conclusions it's arriving at and things like that, which makes it sound like it's a lot more autonomous than it actually is. But essentially, it's a way of understanding how the program is running as it is running, and it can illuminate a lot of problems that may seem mysterious otherwise, thus allowing you to debug much more quickly and efficiently with the Arduino. So we're going to go over that as well. It's going to be a very useful thing in general, even if it doesn't end up being specifically useful for Science Olympiad. So that's going to be that particular focus, and then we'll go over digital and see how digital works and mess around with that, and then that should really do it for the introduction to inputs, and then we can move on to something else and gradually increase the complexity of our circuits and our coding as we understand more concepts. So that should be pretty cool, I think. I hope you guys will think that's cool. Hopefully we'll get to servos and potentiometers, because you can do some pretty neat stuff with that stuff. It's kind of cool to be able to hook up a potentiometer and turn the potentiometer and have the servo turn to mimic it. So we'll figure it out. We'll get as far as we can, and pretty much all the stuff that you learn here will be at least in some fashion useful. So don't despair. So anyway, for our analog read circuit, we're going to be using a photocell, also known as a light-dependent resistor. And I think I spent some time talking about this on Thursday because these things are pretty neat, and I was pretty excited about it. The light resistance, as the name implies, the light-dependent resistor changes its resistance depending upon the amount of ambient light. The more light there is shining on the LDR, the less it resists in a circuit. So if the lights are off, it's a very, very effective resistor. If you've got a flashlight shining directly into the thing, it's going to let a lot of power through. It's not a very strong resistor in that case. In that situation, it's actually it can go to almost close to a zero resistance value. Obviously, nothing's perfect. But it can act sort of like bare wire in that respect. If you've got a very bright source of light and you've got a very sensitive LDR. So, without further ado, let's go ahead and let's build that circuit in circuits.io. Well, I'm going to build it in circuits.io. If you have a physical Arduino and you have an LDR, you can build a physical circuit for yourself and then test it out on the Arduino and everything like that. If you have circuits.io like I do, it'll work just fine. Don't worry, you'll be able to use an analog component and simulate analog input and everything like that, and you'll be able to basically see everything that's going on. So here we go, circuits.io. I didn't need to type it all out because Chrome already knows, because I've been to the site so many times in the last year. And we are going to create a new electronics lab, just like we've done a few times now. We'll let it do its thing and load. And I'm going to drink some water while that's happening. Oh, it's already done. Still going to drink some water though. And we're going to set up our circuit just like we have before. We're going to drag out an Arduino, an Arduino Uno R3, just like we have in the past. And let's see what else here. We're going to have a 10,000 ohm resistor and a 330 ohm resistor and an LED and a photoresistor. So let me go ahead, delete all that. So we've got our LED and our resistor, so we're going to drag out two resistors, one LED. And I'm going to search for LDR, see if that pops up. Photoresistor, LDR, boom, right there. It's going to be this weird bronzy looking thing with the what looks like an inductor symbol on it. It actually just looks like a picture of an LDR, because that's what they look like in real life. And that's going to be everything that we need in order to do our analog circuit. So let's go ahead and get this hooked up. So first off, let's set our resistors to be the proper value. One of them is going to be 330 ohms and one is going to be 10,000 ohms. So I'm going to go ahead and set this one to be the 10,000 ohm resistor. I'm going to zoom in so you can see how the bands change. So bam, it's already set to thousands of ohms, so we just set it to 10. And as you can see, we got a brown on black, one on a 0, and an orange, which signifies 1,000. So we've got 10,000 ohms here. Then on this one, we're going to set this up to be 330 ohms. 330, and then change the drag down, little drop down menu, so it's regular ohms instead of kilo ohms. So now we have a 330 ohm resistor and a 10,000 ohm resistor. Then we've got our LED and our photocell and our Arduino. Let me rotate the Arduino so it's facing in its proper direction. Of course, there is no real proper direction. It's just something that I like. I like having it hooked up like this more. It looks neater to me, as in more tidy, not as in neat, cool, awesome. And let's go ahead and hook up our circuit. So let's see here. We don't even really need the LED, but we can totally do it anyway. So we got our 330 ohm and our 10,000 ohm resistors and our LED and our photocell. So what I'm going to do is I'm going to hook up my photocell across two rails, just like always. Nothing surprising there. Obviously we have to do that, otherwise we're going to short circuit. Then I'm going to hook up the 10,000 ohm resistor to one end. Now here's the interesting thing. If we look at the diagram here, the 10,000 ohm resistor actually has two sets of things hooked up on it. Good Lord. Two sets of jumper cables, or wires hooked up to it. Jumper cables are a totally different thing. One of them, let me just go ahead and wiggle around all this stuff. Boom, boom, boom. This is a little bit more complex than it probably should be, but this way there's no confusion as to whether or not it's hooked up to the ground. So as you can see, it's running through the 10,000 ohm resistor, but then it's kind of like that there's a crossroads here. The electricity can either go over the resistor or it can go down this jumper. As it stands right now, it's always going to go down the jumper because there's nothing hooked up over here, so it's not going to, there's no completed circuit. But let's fix that. Let's draw one right here. And we'll make this one a black wire because it's running to the common ground. And then we can hook the common ground up to the ground on the Arduino. Bam. Just like so. Now, keep in mind that this is separate. Then we're going to have, let's see here, should we do 3.3 or 5 volts? We'll do 5 volts. We'll go with what they recommend. So I'm going to run 5 volts from the Arduino to the common power. Make it red to signify that it is going to be power. And actually, I'm going to since it's clear enough that it's not actually connected to anything, I'm going to go ahead and get rid of that additional turn in order to clean this up, because we're going to have power run from the common power to the LDR. So as you can see now, we've got a fully completed circuit as it stands. Power is going to travel down the 5 volt. It's going to travel up the common power, travel down this jumper cable, jumper wire, over the LDR, and it's going to have a choice. Either it's going to go this way and out to the ground, or it's going to go down this way and into A0. Now, based on this, what direction do you think the electricity is always going to go in? Yeah, it's pretty much always going to go into A0. So this ensures that we're going to have, you know, a input always going down A0. Now, you might be asking, why don't we just not have the resistor here? Well, the resistor here actually helps complete the circuit otherwise, and strangely enough, it actually helps ensure that there's always power running across the LDR. It's sort of a weird phenomenon in electricity, and to be perfectly honest with you, I don't entirely understand it either. But the important thing is that this helps draw some of the power out of the circuit and make sure that, you know, we still have a complete circuit, even though, you know, we may have some words. We have a lot of resistance on the LDR. Then we're going to hook up our LED to one of the digital outputs on the Arduino. And this will be interesting, and you'll see why in a moment. So I'm going to rotate it. Let's figure out that's going to be our anode, and this is going to be our cathode. So we're going to hook up the resistor. We'll move everything down a little bit. So bam. And we're going to hook this up to the ground. And we're going to run from 3 onto the resistor circuit. And we're going to keep this one, we're going to make this one purple. So we got some crossing wires, and that's kind of weird. And you might be like, why aren't we running from 2? Because it's a straight shot. Like, why do you have this 3 and then the weird little juke here? Well, you notice how we've got this little tilde or whatever right next to the 3? And then we've got this right here, which says PWM, and it has the same little symbol. Well, it's a little key. It's signifying that anything that has the tilde next to it sends out a pulse width modulated signal, or uses pulse width modulation. What a big fancy term. What does that mean? Well, think back to our explanation of the difference between digital and analog, right? Digital can either send out 1 or 0. Analog can send out anywhere between 1 and 0, including 1 and 0. Sometimes, though, you only have the ability to send out a digital signal, but you want to be able to send out an analog signal. Well, you're kind of stuck, right? Like, that's not possible. You can't do anything about that, right? Well, not quite. Enter pulse width modulation. Let's take apart what that means, first of all. So let me refer back to a graph of electricity where we've got 0 volts, and let's say this is 3 volts. So it can either send 3 volts or it can send 0 volts. Remember our little light switch analogy? Okay, actually, yeah, let's remember our light switch analogy. So let's say you have a light switch sitting in your room, but you kind of want to run dimmer lights than normal. Fluorescent lights, right? You know how fluorescent lights take a little while to turn on? Like they do that thing where they kind of start to buzz, and then they're dimmer than normal, and then they sort of warm up a bit, and the gases in them start to conduct electricity better and everything, and then the light comes on full blast, but there's usually that warming up period for the light. Everything essentially does that. It's just other light sources do it fast enough that we don't actually see it with our own eyes. Now let's imagine in this thought experiment for a second, we could see it with our own eyes. Every time you turned on the light switch, that could be considered a pulse. So every time the graph is high, that is a pulse. Now let's say you could turn that light switch on and off a few thousand times a second because you're Superman and you have super speed, or you're the Flash, or whatever. Insert your superhero of choice that has super speed. So you can turn on and off that light switch a few thousand times a second. Obviously, since you have perfect control over this, you could turn that light switch on and off a few thousand times if you wanted to in a second, or you could turn it on and off a few hundred times a second. It doesn't really matter to you. But you turn it on and you keep it on for a little bit longer and then you turn it off. So, I mean, you do this in slower time anyway. Sometimes the light is on in your room for a few hours longer because it's the winter time and so it gets dark earlier, you know? Or it's the summertime and it gets dark later, so you have the light on for less. So we can take a look at how long the light is on. So we're taking a look at how long this pulse is right here. And we're measuring its width. This is the width of the pulse. I mean, that sounds weird, but it makes sense, right? You're measuring the width of the pulse, how long it's been on, by taking a look at how wide that plateau is in a graph. So that is the width of the pulse. Now, let's go back to our little thought experiment where you could turn a light on and off a few thousand times a second. If you could do that, presumably you could also see the light warming up and getting brighter. However, what if you turned it on, but you never kept it on long enough for that light to just stay, fully warmed up, to ever get fully warmed up? It was always just starting to warm up, and then you flipped it off again, and you let it cool down, and you flipped it back on again. So like something like this, where the times on are much shorter than the times off. This is where modulation comes into play. That's essentially just a really fancy word for control or change. Pulse width modulation is just a fancy term for controlling how long you keep something on for. So in our little thought experiment where you turn the light on and off and you don't ever let the light warm up, the light's never going to get that bright, right? Because as soon as it starts to get a little bit brighter, you turn it right back off, let it cool down, and turn it right back on, so it has to go through that whole warming process again. Now let's snap back to normal person time, the time that you and I normally perceive. And you've got somebody flipping the light switch a few times a second just like going nuts on the light switch. Let's ignore that right now because that's actually probably a pretty disturbing image. And let's look at the light bulb. All you're seeing, because this is happening a few thousand times a second, is a dim light bulb. You're seeing it turn on and warm up a little bit. You're not even seeing it like start to warm up. You're just seeing it get like kind of bright and then it's off. And then it's kind of bright and then it's off and it's kind of bright and it's off and it's kind of bright and it's off. Except it's flipping between on and off so quickly your eyes don't even perceive that. So for you, you're just looking at a slightly dimmer light. By changing how quickly you turn something on and off and how long you keep it on versus how long you keep it off, you can simulate an analog signal. To our untrained human eyes that can only perceive things in, you know, in I don't know, centiseconds. I mean, we can perceive milliseconds, but anyway, not like necessarily like I'm talking here. The effect is the same as if we were just sending a little bit less power through light, because it's kind of essentially what's happening. We're not giving it the opportunity in order to turn on all the way. So if we were to look at a graph of like the average power that this received over time, by math trickery, it would be less than full power. Anyway, this is all a long and drawn-out explanation to say that we can use digital signals to fake an analog signal. If we kept it on for longer than we kept it off, that would be kind of like sending almost full power. If we kept it on the entire time, obviously that would just be like sending it full power. If we kept it off the entire time, it'd be like sending it no power, because it's exactly what we're doing. But it's these spaces in between that allow us to sort of simulate an analog signal. Hopefully that made sense. Basically, pulse width modulation is just a fancy term for turning the power on and off really fast and pretending like it's an analog signal. So the Arduino can do that. So we can utilize pulse width modulation on the digital side in order to simulate an analog output. So we can take our analog input and we can send an analog output, sort of, on the LED. Now, we might not actually end up doing that with the coding, depending upon, you know, how much time we ended up having and everything like that. We might just look at the serial print and the serial monitor and everything like that. But we can get that done. That'd be pretty cool too. But anyway, that should be our completed circuit. As you can see, we've got our LED plugged in. It's plugged into the resistor, and the resistor is hooked up to the ground. We've got our photoresistor, our photocell. Photoresistor. Photocell is a different thing. We got our photoresistor hooked up to 5 volts, and then it's hooked up to a 10,000 ohm resistor as well as analog A0, and then the 10,000 ohm resistor is hooked to the common ground. So with that, we actually should be able to get started on the programming side of things. So let me go ahead and open up the Arduino software. Bam, bam. Bam. Helps if I double click. There we go. There's actually no... Okay. All right, so I've got my Arduino software open. And thinking back to the 2 things we need in every single Arduino code, what are those? I know this is repetitious, but it helps solidify it in your brain. Exactly. Setup and loop. So let me go ahead and bam, 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 bam. So now we got our void setup and our void loop. Now, I believe we need a pin mode, but let's go ahead and check that. We do, in fact. So just like always, so notice how I skipped establishing a variable for the pin. Why did I do that? I mean, there are a couple of reasons why I did it, but that's actually one of them. But there's a secondary reason. So its analog is the root cause, but there's another one that goes into variables that explains why we wouldn't be able. Not only that we didn't use a variable for this, but we wouldn't be able to. Note the name of the pin. It's A0. That's a 0. Let me put a little slash through it so I can distinguish it from an O. Remember what I told you about variables? What's one thing that variables need to be in the Arduino programming language? Well, initialized and have a value, yes. But let's think about, why would I initialize a variable with that? To tell what type of variable it is. Now, what's the caveat here? What can I only put in this? Exactly, integers. Whole numbers, right? So we wouldn't be able to put an A in there because A is not a number, it's a character. So we would be able to do like a string variable that could hold A and 0, but then it would be fed differently to this, and it would take some technical wizardry to make it work, which would honestly just be way more trouble than it's worth. So for that reason, we just feed A0 directly into pin mode because pin mode can take that. Now, in addition to that, I did it just because we don't actually need to have a variable keeping track of what pin it is. In fact, we're going to do something that's a little bit easier. We're going to say int l. Really throws me off my game. That shift delete is the same thing as, or shift backspace is the same thing as delete, because this is like literally one of the only programs that I use that does that. And sometimes if I'm typing something with capital letters, I'd like to keep my finger down on the shift key so I can just correct a minor error and continue typing in caps. But anyway, that's just me belly aching. int ldr equals analog read A0. So here's what we're doing right here. We are using a variable, but we're dumping what the Arduino is taking in on A0 into that variable. So the Arduino reads, I don't know, 125 onto A0. And it goes, okay, and it stores that in memory in our LDR variable. So now we are done with referring to the pin. Anytime we want to use the value that comes in on A0, we refer to the variable that holds onto it. But here's the thing. If we were to upload this and put it into to the Arduino right now and run it, we would technically have a complete program and it would run just fine. But we wouldn't be able to tell it would look like nothing's going on, and why is that? Well, that's the thing. The Arduino's doing stuff. The code's doing stuff, technically speaking. But you might be referring to visible outputs when you say that. Yeah, exactly. There's no outputs. We're doing input and we're storing it, and the Arduino is just is dutifully taking that value and storing it inside of its RAM, or registers, I guess. Whatever. I don't remember offhand if it actually has RAM. It might just have registers. Anyway, it's taken this stuff. It's got to have RAM. No, it doesn't really need that much. That's neither here nor there. It's taking this stuff and it's storing it in memory, but it's not doing anything with it. I mean, it's doing this. It's doing this every cycle, and so it's busy. It's doing stuff, but we can't tell because we can't see that stuff. So we need to do something in order to make it visible. We need to have some sort of output that we can look at and go, okay, you know, our Arduino's running as expected, or it's not, or it's on fire. I mean, that could be an output. Although I would probably try and not make the Arduino catch fire. And there's no real code in the Arduino programming language to make it do that anyway, because a lot of people don't really recommend that. So that's out. We can make the LED light up with the value of LDR. So let's go ahead and do that. In fact, actually, we need to set up another pin mode. 3 output 2. There we go, output. And we're going to go analog write 3 LDR. Bam. So now we're actually, you remember with digital write, it had to be the pin and whether it was high or low. Because now we can send a value, any value between 0 and full, we have to specify a specific value. Thankfully, we're getting an analog read value already in an A0 and storing it in the LDR. So we can take that LDR value and then just write it to analog. We can analog write it out on 3, which is our PWM pin. So let's go ahead and we'll upload this to our Arduino in circuits.io. And let's see what happens. Paste. And upload and run. So now if I click on my LDR, I get a little meter while it's running. And this little meter has a little black circle on one side and a white circle on the other with a whole bunch of lines coming off of it. As you probably already guessed at this point, this signifies the amount of ambient light that the LDR is receiving. It simulates that. So we can drag up the meter in order to simulate more light. So let's go ahead and do that. But there was no real change with the LED. Nothing really seemed to be different. I mean, you can kind of see it. It's very, very difficult to see, though. So this seems not ideal, right? Bright. Vaguely, slightly less bright. Bright, sort of, kind of, not really as bright. Well, that doesn't seem to be working as expected, right? This might be a case in which yours won't work. Well then, haha. Will it not compile, or do you get like an error readout and any highlighted lines when you try and do that, or does nothing happen when you run it? Okay, so the LED does not light up, is what you're saying. Or do you not even get this, like, does the simulation not even start? Do you just have no simulation running after you upload and run? Oh, there you go. Look at that. You didn't even need my help. You're well on the path. Okay, so yeah, so this isn't working like we really want it to. So let's figure out what exactly is going on. And for that, we're going to utilize serial print. Now, serial print is a framework that allows us to view the data that the Arduino is processing. There's not really much that it does on its own other than print stuff to a serial monitor. And that's really all it does. However, the fact that it's actually well, let's test out the serial print and see if that doesn't illuminate what the issue might be. Because it's such a bare bones little framework, it's basically just a means to an end so the Arduino can send some information out to the computer and we can look at it. It means that we can customize that information that's sent however we'd like. So we can have it be very useful information or very useless information. Serial print is really only as useful as you make it when you're setting it up. So it's a very valuable skill to have to be able to pinpoint what exactly you want to see, what kind of data you want from the Arduino, and print that information out to help you out. It's not exactly like super deep, like debugging. You know, when you're working with code in the computer and stuff like that, IDEs will have basically little emulation environments that'll allow you to set up breakpoints and things like that, and then view what's going on in memory and watch it change from like line to line in your code and from frame to frame and whatever you're running. And it's pretty intense. This is not anything like that, but it's actually it can be a very powerful tool if used correctly. So let's take a look at a couple of the commands that serial print uses. First one is serial.print. It'll print out whatever's in the parentheses onto the screen. Now, the way serial print works is if you have multiple serial prints in a row, it'll just slap one right after the other. Just like imagine you're using like text edit without word wrap, and you just keep typing and typing and typing and typing and typing and typing and typing. And they'll just be one right after the other, no spaces, and you know, it will eventually actually wrap down because it won't go off the screen like it will in text edit or something like that, but it will just continue printing it horizontally. Now you've got print ln, which is short for print line, and that after it prints something out, it will print a new line. So you can use it to actually format your data a little bit better and make something look a little bit prettier and easier to read. So usually canny utilization of serial print will have a combination of serial print and serial print line, allowing you to format the information to something that's very easy and useful for you to read. So let's go ahead and let's add this into our Arduino code. Now there's one other command that we're going to need, and it's serial.begin. And I'm going to put 9600 in the parentheses. Now this serial.begin basically opens up a port on the Arduino to communicate with the computer. This is something that you need anytime you're using serial print. Otherwise, your Arduino won't actually send any data out on that port. Your computer won't be able to communicate with it in that way, and you'll see nothing pop up on your serial monitor, and you'll be like, well, why isn't it working? And that will be why. Now, also keep in mind that anytime I'm using any of the serial commands, the S is capitalized. So this is capital S, E-R-I-A-L, and then a period, and then the word begin, all lowercase, and then in parentheses 9600. Now this is just the port and the baud rate. This doesn't have to be 9600, but this is a nice starting default value that the Arduino can send stuff out on. Sometimes 9600 isn't going to work, in which case you can use one of the other rates. But for us, we're just going to use 9600. It should work just fine, because that's pretty much the default one. So we got serial.begin 9600. Now, let me go ahead and serial.println LDR, just like so. So what's going on here, again, capital S, serial.println, the value of LDR. This is just the raw value for LDR. So each cycle of loop in the Arduino. It's going to fill LDR with a value from A0, whatever value is A0 at that particular moment in time, and then it's going to slap it onto the serial monitor. And then it's going to analog write it to pin 3. So let's upload our updated code to our Arduino. Hello? All right, simulation's running. Boom. I'm going to open up the serial monitor over here. As you can see in the code window, we've got a serial monitor on the right-hand side. And I can not expand it, which is not exactly useful, but oh well. And I'm going to upload and run the code. Uh-oh. I forgot about the closing curly bracket. So let me try and uploading it again after fixing my error. Bam, bam, bam. Now, as you can see over here in the serial monitor, it's just spitting out values like crazy, and they're all just 54s. But if I drag the slider on the LDR, the values change. What is the resistance for which resistor? Okay, so this one is 330. The one circled in red is going to be 330 ohms, and the one circled in blue is going to be 10,000, 10K. So yeah. Oh, there you go, Jacob. It's one of those paradoxes. I've done that so many times, and you feel like simultaneously the smartest person and the doofiest person in the world. Smart because you figured it out on your own, and then doofy because, oh, geez, there's just no power connected to the breadboard. Yeah, yeah, and it's the same deal in coding. It's just dealing with this kind of stuff in general. Whenever you're making things, you're like, why isn't it working? Oh, right, I forgot like one of the most basic things that you need in order to get this thing running. Duh. But go me for figuring it out. So yeah, I've been there. I've been there a lot. But here's the other thing. You troubleshoot it on your own. Troubleshot. Anyway, you did the thing where you troubleshoot it. Yeah, exactly. And that's the whole point. That's like at least half the competition right there is just debugging. So yeah, there you go. Anyway, watching the serial monitor over here, now it's spitting out 974 because I tuned it all the way down here. Now if I go about halfway, I can see the values change to 932. If I go there, let's see, it's all the way down to 54 again. So I can see that the values are updating, and they're actually updating with some pretty extreme ranges. Now, I happen to know offhand that analog writes a value from 0 to 255. It doesn't go higher than 255, so if you feed it a value higher than 255, it's going to cap itself at 255 because that is basically the range of values that can be sent out through pulse width modulation. So we start at 54, which is about a fifth of the way, and then we jump straight up to 900, like next you know. So we're going from 0 to full power. We're going from about 1/5 to full power. So the range has been greatly reduced for the LED. If we were to, say, affect the values that are coming into analog read, or the values that we have in LDR, to something that's more useful for our analog write, we would actually be able to see a better range of brightnesses coming out from that LED. So let me go ahead and do that real quick. This is my LDR up here. or photoresistor. It's got a couple of names. LDR is short for light dependent resistor. There's also photoresistor. If I click on it while the simulation is running, I get that little slider, which is supposed to be circuits.io's way of simulating ambient light. If you were using a real LDR, you would basically either be shining a flashlight on it or putting your finger over it to increase or reduce the amount of ambient light. Oh, there you go. Yeah, that would be, there you go. Hey, troubleshooting. Okay, so I'm going to utilize a bit of coding that you guys will probably see later on in these lessons, but I'm going to introduce it to you a little bit early. I don't think you're ever really going to see it when you're messing with like Arduinos in the with the debug part or anything like that. Wow, that took a lot of work. From low, from high, too low, too high. Okay. So it's called the map function. Boop. Let me just delete that again. So I'm going to, basically the way it's structured is such. The command is map. And it takes in 5 values. The first value is the input variable, the input variable. The second value is essentially the lowest value that that input variable will feed you. We're going to say 50. I know it was feeding 53, but it's close. It's close. Then the third parameter is the highest value that you'll be reading. So let's go all the way up to 900 and let's say 975, which again is a little bit higher than we were getting, I believe, if I remember correctly, but this will roughly approximate the range that we're getting. If you really wanted to button it down and get like very accurate, you would, obviously be reading that serial monitor and pull in the lowest and highest values that the Arduino would be feeding you, because that's what it's getting from the analog read, and that would give us a much more accurate picture of what we would map. Now, so far we've got the variable that is feeding information into map. We've got the lowest value that that variable will feed into map, potentially, and the highest value that that variable will feed into map, potentially. Then we've got the lowest value that we want mapped to outputs, and the highest value that we want mapped to outputs. Let's actually make that 254. And then we've actually got to set it all to something. So we're going to say int LED equals map. So now we've got another variable that we're feeding these map values into. So what it's doing is it's taking that raw data from LDR, which could be anywhere from somewhere around 50 to anywhere that's somewhere around 975, and we're remapping those values. Basically, we're taking this and we're saying, okay, so 50 is the lowest value we can receive, right? That's going to be equal to 0. We're going to convert that to 0. 975 is the highest value we can receive, right? So we're going to be converting that to 255. And anything in between, basically create a smooth graph that kind of fits that. So if it's around like 470 or so, then that's roughly equivalent to 127, because that's about half of 255. So about halfway between 50 and 975 would be about halfway between 0 and 255. If we were at, I don't know, 600, that would be somewhere around like 180 to 200, because I can't exactly do the math perfectly in my head right now. Point being, it basically, constrains those values and sort of creates a smooth equivalency. Then we're storing it in LED, and then we're feeding that value. So we should be pretty much guaranteed that the LED is only going to get a range. The analog write on pin 3 is only going to get a range between 0 and 255. And this means that we're going to have a much smoother set of values that are fed to our LED. So let me copy and paste that stuff in there. Upload and run. I forgot it again. Blair. There we go. Upload and run. So now, as we can see, our LED is much dimmer. Much, much dimmer. Not entirely off, but much better than it was before. And if I turn it up, look at that. The LED, there's a much greater difference between the LED at full off and full on as far as the LDR is concerned. So now we've actually made our LED much more recognizable in this whole thing, just using that one command. Now that may not have made perfect sense right now, and that's okay. We'll spend some more time. I'll probably spend some more time explaining map in the future as we get further along, perhaps with more MS Paint graphs for your viewing pleasure. But as it stands right now, it's 2 minutes till 9, so I'm going to go ahead and do the poll questions, and then we'll leave it open for question and answer time, and then we'll break for the next couple of days and meet up again on Thursday. So
I'm also here as well if you have questions regarding the Science Olympiad event or equipment or hardware.
I didn't even see you enter, Mr. Dubik. So there you go. If you've got questions about what we went over today or Science Olympiad in general, we'll both hopefully be able to answer all of your questions. So let me go ahead and get started with the poll questions, and then we'll do question and answer time.